Here we are with another new video. In this video, I will be solving the last year physics exam for grade 11 advanced. So in this video, I will be covering three chapters. First, the kinetic energy, work and power. Second, the potential energy and energy conversion. And third, momentum and collisions. So here we go with question one. So which of following expressions represent the law of conservation of total momentum? So to answer this question, you have to refer back to chapter 7, section 3. And here is another example of a collision. So we have two balls being collided. So as we know that before being collided and after being collided, the momentum is always constant. It's always the same. So you can find that out, that potential momentum before the collision initial is equal to the final momentum after being collided. So option 1 or answer 1 is the correct one. We continue to question 2. If positive work is being done on an object, which of the following statements is true? Also, to answer this question, we have to refer back to chapter 5, section 3. It's written that work is the energy transferred to or from an object as a result of a force. So positive work is a transfer of energy to the object. So positive work is a transfer of energy to the object. And negative work is a transfer of energy from the object. So positive work means that the object is receiving energy. So which is equivalent to the first statement where energy is being transferred to the object. So that's what we mean by a positive work. We continue with question 3. A conservative force is moving an object from a point A to point B, then back from B to A, as you see here in the picture. So from A to B first, and then the other way from B to A. Which of the following is not true? So all of these are correct except of one. So I advise to refer back to chapter 6.2 to answer this question. You should know three main ideas about conservative forces. First, they are path independent. So wherever the path is, so the force is constant. Second, the mechanical energy is always conserved, so there is no dissipation of energy. And lastly, the work done from point A to point B is equal negative of the work from B to A. So we can cancel some of these options. So total mechanical energy is conserved for the object. Yes, it's conserved, but they're asking us to find the false statement, which is not true. So this statement C is true. What about that one? The work done from A to B is path independent, which is equivalent to option A. So D also is true. What about option B? The total work done on an object is equal to 0. Also, the total work is equal to 0 as equivalent to the third idea here. So we still have the first one where work done from A to B is equal work done from B to A, which is wrong. It's supposed to include a minus here. So option A is the answer in that case. We continue with the next question. A wagon is pulled with a rope that makes an angle of 30 degrees to the horizontal, as shown in the picture. So this is the picture. A wagon or a box being pulled forward with an angle of 30 degrees with a force tension in a rope which is 50 Newton. What is the work done by the force if it moves 100 meters on the horizontal surface, as stated here? So to solve this question, you need to apply this equation where work is equal to the force multiplied by distance multiplied by cosine the angle. So force in this case is 50 Newton multiplied by distance 100 by cosine 30. And the answer is 4,330 Newton. So which is equivalent to the first answer here. But here I don't know why it's flipped. So it's 4330. Next, with the next question. So in a physics lab, a student uses a frictionless wheeled cart in an investigation. He loads the cart in each time with a block of different mass and applies the force, the same force of the cart to move it from the same distance, d. So here we continue with question 5. In a physics lab, a student uses a frictionless wheeled cart in an investigation. He loads the cart in each time with a block of different mass and applies the same force F to the cart to move it from the same distance d. In which of the following trials the cart will move faster? In which one the cart will move faster at the end of distance d? So here we have three options or three trials. So in each one, the boy is adding a block of mass to the experiment. So in which case, the cart will move faster. So according to Newton's second law, where A is equal force over mass. So every time we increase the mass, we decrease the value of mass, we have more acceleration. So of course, the cart will move faster where mass is very low. So the cart 1 or trial 1 is the correct answer in this case, and the cart will move the faster. We continue with the next question. In which of the following cases the total work done on a car equal to 0? So that's the equation of the work, which is force multiplied by distance. Let's assume the angle is 0. So the force is, according to Newton's second law, is equal mass multiplied by acceleration multiplied by distance d. So this equation could be equal to 0 in both cases. So first, if the distance is equal to 0, there is no displacement, or if acceleration is equal to 0. Acceleration equal to 0 means the velocity is constant, which is equivalent to the first answer. The car moves with a constant velocity. So the work is equal to 0 when the velocity is constant. We continue with the next question. Anas uses a horizontal force of 20 Newton to push a 4 kilogram box along the horizontal surface for 3 meters. Then lift the box up to a shelf of 100 meters high. What's the total work done on the box? So that's the picture where first the boy pulls the box 3 meters horizontally and then lift it for 1 meter. So we have to calculate the work, total work in that case. So let's divide the problem to two sections. So first, from the work done from point 1 to point 2, 1 to 2, plus the work done from point 2 to point 3. So first, from 1 to 2, it's force multiplied by distance, which is 20. The force applied is 20 Newton multiplied by 3 meter, plus the work done from 2 to 3, point 2 to point 3, which is mgh. The mass of the box is given 4 kilogram, ng 9.8, and displacement in that case is 1 meter. So the answer is 99 joule. We continue with question 7. When a mass m is attached to a spring with a constant k hanging vertically, the spring is extended for 12 centimeters. If the same mass is attached to another spring with a constant of 3k hanging vertically, for how much length delta x it would be extended? So here we have a spring first with a spring constant k, and then with the same mass attached, the spring now has a 3 times more spring constant. So let's go back to the equation of Hooke's law where F equal kx. So the displacement x is equal force over k. So in the first case, the displacement is 12 centimeter is equal to the force over k, the spring constant. As they said, the force is always the same, not changed. What's changing here is the spring constant. It's 3 times more powerful now, the spring. So we divide it by 3. So of course, in the second hand, 12 also is supposed to be divided by 3. So the displacement in that case is 4 centimeter. We continue with question 8. Modern cars are designed with airbags to reduce damage during head-on collisions. How do airbags work to reduce damage? So I prefer if you can go back to chapter 7.2 to understand that question. The function of airbags is to reduce the force. So that's the main idea of airbags. So there is an equation in that chapter stating that the force is equal to the impulse over delta time. So remember, in the case of airbag, the force is supposed to be reduced. How to reduce the force? Of course, by increasing the time of collision, because F and delta T are inversely proportional. So we have to increase the collision time to reduce, in order to reduce the force. We continue the next question. A ball with a mass of 0.2 kg collides with a wall with a speed of 10 meters per second at a right angle and rebounds with the same speed in the opposite direction. So it's going right on a right angle to the wall and then go back to the same direction. If the contact time between the ball and the wall is 0.1 seconds, what is the force exerted on the ball by the wall? So these are the given. The mass of the ball 0.2 kilogram, saying that the same speed before and after, so V final equal V initial equals to 10 meters per second, and the time of collision between the ball and the wall is 0.1 seconds. It rebounds, or it goes back with the same speed. So to calculate the force, of course, you need to apply the same equation as the previous question, where F is equal J over delta T, and as you know, J, which is the impulse, is equal delta P, the change in momentum over time. So let's discuss it. So delta P means a momentum final minus the initial momentum. So mvf, and let's consider this vf, the ball when it rebounds back, minus, because it's going in the opposite direction, minus, so we have double minus, the first one from the equation and the other one from the direction of the ball, so they cancel each other, and the answer is 2mv over delta t. Here vf equal vi, so it's 2mv over delta t. You replace you put the values, and the answer is 40 newtons. We continue with question 10. A crane developing 8,000 watt raises a car of 1,600 kg for 10 meters vertically at a constant speed. How much time does it take to complete this task? So to answer this question, asking for time, and the power is given. So so how to calculate the time? By arranging the equation, which is equal to energy over the power, because it's they saying it's the car is moving vertically, so we have to use the potential energy, which is U, which is equal to mgh over the power, which is 8,000 joule. So the mass of the car multiplied by the gravity multiplied by the height 10 meter over the power, and it took the crane 19.6 seconds to raise the car to 10 meter. The next question now. Which of the following is a correct unit of power? So also the same equation, where power is equal energy over time. Let's consider here the kinetic energy, which is half mv square over time. So let's convert this to units. So mass is expressed in kilogram, and velocity is meter per second, and we put square because of the square here, over the time, which is in second. So we end up in this equation, kilogram by meter square over second cube, which is equivalent to the first option. With the next question now. A car of mass 1,800 kg starts from rest and reaches a speed of 30 meters per second in 10 seconds. What's the power that the car's engine during this period? So we have the mass starts from rest, means the initial velocity is equal to 0 and final velocity is equal to 30 meters per second during a time of 10 seconds. So what's the power in that case? So that's a P. So to calculate the power, again, it's energy over time. It's half mv square over the time, which is equal to 81,000 watt or 81 kilowatt. Again, the first answer is the correct answer. We continue with question 14. A runner in the Olympic Games with a mass of 80 kg has a kinetic energy of 4,000 joule. What's the momentum of the runner? So this is the given, the mass, the kinetic energy of the player, and now we have to calculate the momentum. So to calculate the momentum, you should go back to chapter 7, section 1, where there is a quick way that, or quick equation that connects these two parameters. So the kinetic energy is equal to P square over 2m. So to calculate P, we simply arrange the equation. Now it's the square root of K multiplied by 2m. And the answer is 800 kilogram meter per second. Here we are with question 15. The figure shows the velocity time graph for two cars, A and B, that collided elastically. Elastically means after the collision, each one of them going separately. Which of the following statements is true? So we have lots of information in that graph, and we need to decide which of these statements is true. So the first body or the first car or cart A being collided with cart B. So as you see here, you can guess that cart B has a velocity of 0, means it was at rest before being collided, and the velocity of the cart A was around 1 meters per second. It's coming to the second one. After being collided, both of them, as you see here, are moving. None of them is at rest. So, but look what can find out from the picture, that cart A is losing speed, however cart B is gaining speed. So let's find out which one of these four statements is true. The two cars move in the same direction after being collided. Yes, both of them are moving in the positive direction because none of them goes to the negative area here. The two cars were moving in opposite direction. No, both of them moving in the positive direction. Car B stopped after being collided. No, because none of them reach a velocity of 0 after the collision. What about the last one? Cart A move in the opposite direction after collision. No, cart A is losing some velocity, but it's not moving in the opposite direction. So option A is the correct one. Next, question 16. A billiard ball moving with the velocity of 2.5 meters per second collides elastically with another ball of the same mass at rest. So what's the velocity of the second ball after collision? So you can refer back to chapter 7, section 4 of elastic collision. And you can discuss the first case, or called case 1, where the two bodies being collided have the same mass. So you can say that the final velocity of the first ball is equal to the initial velocity of the second ball. You can look back at this one also. This is a good example. So we have the white ball moving at a speed, and initially the black ball was at rest. So after collision, the white ball now it will be at rest, and all the velocity will be transformed to the black one. This is what we call by exchanging speed. So we continue with the next question. And question 17. A 0.5 kilogram red ball moving in a straight line at a velocity of 1.6 meter per second collides elastically with a 0.3 kilogram blue ball at rest. So what's the speed of the blue ball after the collision? So again, let's apply the law of conservation of energy, of momentum, sorry. So the momentum before is equal to the momentum after. So we can say, or we can apply special case 2 because one of the object is at rest. So we can directly apply that equation that we learned from chapter 7 section 4. So the velocity of the second ball, or the blue ball, is equal double the mass of the first ball over the total mass of the red plus mass of the blue, multiplied by the velocity of the first ball initially, and the answer is 2 meters per second. We continue with question 18. An astronaut of mass 90 kg in his suit is at rest in space. He fires a thruster that expels 45 multiplied by 10 minus 3 kg of hot gas at 800 meters per second. So what's the speed of the astronaut after firing the thrust? So here, of course, we have to apply the law of conservation of momentum, and we have to calculate the velocity of the astronaut after he hit the thrust. So of course, the momentum before equal momentum after. So we consider the momentum before is equal to 0 because none of the astronaut or the bullet or the throat is or are moving. So there is no momentum, no motion. Equal. After he pulled the trigger, the mass of the astronaut multiplied by its velocity minus the mass of the bullet multiplied by the velocity of the bullet. So here we consider it as minus because both of them are moving in opposite direction. So to calculate the velocity of the astronaut, so you simply arrange the equation and the answer will be 0.4 meter per second. We are approaching the end of this video. So here we are with question 19. A roller coaster starts from rest at a height of 10 meters above point A. As you see here, point A. If the work done by frictionless force is negligible, what is the speed of the roller coaster at point A? So here we have two positions. So where we have the first point and the second point. Of course, we have to apply the law of conservation of energy. So the energy in that position, energy in position 1 equal to the energy in position 2. So in position 1, it's about mgh. There is no velocity. It's all the energy is called a stored energy. It's about gravitational potential energy. So it's mgh equal the energy in the second position. So here there is no height in the second position. So no potential energy. All the energy now is being transformed to kinetic energy, which is half mv squared. So to calculate the velocity at the second position, it's equal to 2g, square root of 2gh, and the answer is 14 meters per second. And here we continue with a bullet enters a wooden block with a kinetic energy of k0 and loses half its velocity as it goes out of the block. What's the kinetic energy of the bullet when it goes out? So an important information here where the bullet loses half of its velocity. So let's say make a small drawing of that where the bullet goes out from the wall and loses half of its velocity. So initially it was moving at velocity v, and the kinetic energy was half mv squared. Now in the second case, the velocity is divided by 2, so the kinetic energy in that case is half mv over 2, all of that is square. So the half, now because of the square, now turns to divided by 4. So the correct answer, the kinetic energy is supposed to be divided by 4 when the velocity will be reduced to half. We continue with question 21. A 500-gram ball is thrown vertically up from the Earth surface with initial kinetic energy of 147 joule. So what's the maximum height the ball reaches? So here we have a ball going high in the air. The initial, the mass of the ball initially was 500 gram. So of course, when you throw the ball has a high kinetic energy and start to lose that energy and transform it to another form of energy, which is called stored energy, where the velocity is equal to 0. So we have to calculate the height in that case. We need to apply the law of conservation of energy. So the energy before you throw the ball is equal to the energy at the top, where at the highest point. So first of all, the kinetic energy is equal to the stored energy. So kinetic energy, which is half mv square, or no need to convert it to half mv square because it's given here, 147. So it's equal to mgh, the mass of the ball. Of course, you have to convert it to kilogram, multiplied by gravity, multiplied by h. So h here in this equation is the only unknown. So after arranging the equation, h will be 30 meters. So we continue with question 22. A block with a mass of 2 kg slides at a constant velocity of 0.5 meters per second on a frictionless horizontal surface, as shown in the figure. So this is the mass, we have the velocity. Okay, when the block collides with the spring, it comes to rest, and the spring is compressed to the maximum value. So there is the spring, the mass moving to the spring, and of course when they hit each other, the spring will be compressed a little bit. So the question here is to calculate that compression, the distance between the first and the second position of the spring. So this is what we need to find, delta x. So how to calculate that distance? So of course, going back also to the law of conservation of energy, of course delta E is always equal to 0 because energy is conserved. So we have to calculate, or to put the kinetic energy first, in the first case, is equal the energy at the last position. So here we call it the work done by the spring force at the last, and the second position here. So half mv squared, the motion of the body, half mv squared, equal to half kx squared, the energy stored in the spring. So to calculate x, you have to arrange the equation. It's the square root of mv squared over k, and the answer is 0.05 meter, or 5 by 10 to the power of minus 2 meter. Here we are with the next question. A car of mass 1000 kg is traveling at 20 meters per second. If a braking force of 5000 Newton was applied to the car, what is the distance that the car moves until it stops? So stop means the velocity final is equal to 0. So that's the picture, a car moving and then applies the brake and then stop at the end. So the mass of the car is 1000 kg, velocity 20 meters per second, and let's consider the friction force or the braking force is equal to 5000 joule. So to calculate the total distance, we have to refer back to the law of conservation of energy, where delta E is equal to 0. So in that case, we have kinetic energy, and we have the energy done by the friction force. all of them, the sum of all of them is equal to 0. So of course here there is no potential energy. So delta K means half mv F square minus half mv I square. We consider minus the work done by the friction force, or delta E other, that include the friction and heat. So all of them are equal to 0. Of course, half mv F square is equal to 0 because the car stops at the end. So we arrange the equation. We have half mv I square equal the work done by the friction is equal the force itself, 5000 Newton, multiplied by distance. So to calculate the distance, it's half mv square over the force, which is 5000 Newton in this case. And the answer is 14 meters. So the car takes 40 meters to stop. We continue with the last question. Ali is pushing a wooden box of weight 78 Newton for 2 meters on a rough floor using a horizontal force of 120 Newton. So the boy is pushing the box for 2 meters. If the total work done on the box is 190 joule. So what's the coefficient of kinetic friction between the box and the floor? So we need to calculate mu, if you remember mu. So of course we need to use the equation of friction. So the work, of course, is equal force by distance by cosine the angle. Here we have, in this case, we have 4 forces. Force of gravity, normal force, the force of the boy in the blue, and the force of friction. Because that's why we have mu, the one that we need to focus on. So of course 4 forces means 4 work, 4 forms of work. So the total work W net is equal work done by the force of gravity plus the work done by the normal force plus work done by the boy WF plus work done by the friction force. So let's discuss each one by one. The work of gravity and work of normal force, both of them are equal to 0. Why? Because they are perpendicular to the displacement. Because the angle is 90 degrees. At cosine 90 is equal to 0. So work of gravity is equal to 0 plus work of normal force also is equal to 0. Plus work done by the boy. So force of the boy, which is 120 Newton, multiplied by the displacement, which is 2 meters, multiplied by cosine the angle. Here in this case, in that force, the angle is E0, equal to 0. So cosine 0 is equal to 1, plus work done by the friction force, which is mu, multiplied by mg, multiplied by distance, by cosine the angle. Here cosine the angle here in this case of friction is equal to 180. So cosine 180 is equal to minus. That's why we put minus here. So W net is equal to 190 joule, as they said. That's the total work. The total work means the work net. W net is equal to 190 equal the force multiplied by distance, 120 multiplied by 2, minus mu mg, which is 78 Newton, mass multiplied by gravity, multiplied by distance, 2 meters. So mu in this case is equal to 0.32, and the second option is the correct answer. Here we are with the last question. The figure shows a frictionless incline that makes a 20-degree angle with the horizontal. So as you see here, a car is pulled for 500 meters at a constant velocity up the incline. So the car is moving up to 500 meters. If the car potential energy changes by 200 kilojoule, what is the mass of the car? So let's focus on that sentence. Let's focus on that sentence. If the car potential energy changes, potential energy means U and the change means delta. So delta U is equal to 2000 kilojoule. So we continue. So delta U means U final minus U initial equal to 2000 kilojoule. So U initial, as you know, is equal to 0 because the age or the height of the car at the beginning was 0. So U initial is equal to 0. So U final, which is mgh, equal to 2000 kilojoule. So the mass of the car will be equal to 2000 kilojoule divided by gravity multiplied by the height. But there is a small trick here. What is the height here? What is the height reached by the car after 500 meters? So here, as you see, there is a small triangle, and we need to find out the opposite side h to the angle. So the angle and height are opposite to each other. So which function in math have or calculate the opposite side? Yes, of course, it's the sine function. So sine, the angle, is equal to the opposite side, h, over the hypotenuse, which is 500. So h, the height, is 500 multiplied by sine, the angle. So, and the answer is the mass of the car will be 1193 kilogram. Sorry, here it's kilogram. Okay, we reached the end of the video. Thank you for your attention and stay tuned for next videos. I will be uploading some questions or expected questions that might come in that year in physics for grade 11 advanced.